So Milton, your sound seems to be working now, so you'll chair this one.
Okay, yes, I can do that. Let me put my video too, so we see at least some faces around. Okay, so, okay, let's wait just 1 minute to catch our breath again. Okay, so our next talk is going to be by Jiaoyang Huang from NYU. He's going to talk about large deviation principles via spherical integrals, and it's going to be a continuation of the previous talk of Alice. Okay.
I want to thank you for the invitation. So I will continue the topic on large deviation principle and present the recent work joined with Serban and Alice on large deviation principle using the spherical integral. So let me quickly start with 2 classical questions related to Horn. So the first problem, it goes like this. See, if we take a diagonal matrix A1, A2 until AN, and take U to be an n by n unitary or orthogonal matrix. And the first problem is to consider the diagonal entries of U, AN, U star. So which is equivalent to ask what are the possible diagonal entries of a matrix with prefixed eigenvalues. And this question, now it's answered by a theorem long time ago by Horn and Schur. And they have a theorem states that if you consider the diagonal entries of U, A, N, U star, and it's a dimension n vector. And this vector, it's in the permutation polytope generated by the eigenvalues of A, A1, A2 until AN. So basically it's a polytope, and all the vertices, they are some just permutations of A1, A2, AN. So it's the convex group of the sets A pi 1, A pi 2 until A pi n. Pi is in the symmetric group. And for any point in this polytope, actually you can find some U such that the diagonal entries achieve that point. You can easily see it from looking at the diagonal entries of the matrix U, A, N, U star. So if you look at the ith entry of it, it's just sum over uik times ak times uki star, because u is a unitary or orthogonal, so this is just uik square. And this sum over uik square is 1. So this is just the linear combination of those a1, a2 until an. That's why this diagonal entries is in this polytope. However, this shows that any vector which can be achieved in this way must be in this polytope. It's maybe it's slightly harder to show actually every point in this polytope can be achieved by the diagonal entries of U, A, N, U star. So I will not talk about it. And another question is this one, considering the sum of 2 matrices. See, if you fix 2 diagonal matrices AN, which has diagonal entries A1, A2 until AN, and Bn, which has diagonal entries B1, B2, and Bn. And the Horn's problem asks what are the possible eigenvalues of U, AN, U star plus V, Bn, V star. And U and V are just unitary or orthogonal matrices. If we denote the sum by Cn and denote the eigenvalues of Cn by C1, C2 until Cn, the Horn's problem asks what are the possible eigenvalues for this matrix Cn. It's equivalent just see what are the possible eigenvalues of the sum of 2 matrices with the given eigenvalues. So there are many relations among the eigenvalues of A, B, and C. For example, if you take trace on both sides, you will get this trace equality. The trace of AN plus trace of BN equals the trace of CN. Also, there are many inequalities among the eigenvalues of A, B, and C. Like if the the largest eigenvalue of Cn should be bounded by the largest eigenvalue of An plus Bn. So we have C1 is less or equal than A1 plus B1. And this is a special case of the Wiles inequality, which is a bunch of inequality given in this form, Cp plus Q plus 1, less than equal than AP plus 1 plus BQ plus 1 for any P and Q. And it turns out there are many relations the eigenvalues of A, B, and C need to satisfy in order for this to be true. And actually, Huang obtained an explicit set of those triples of indices I, J, K. They are of the same cardinality, such that the eigenvalues of A, B, C they need to satisfy those conditions. Sum over CK, K is in the set K, less or equal than sum of AI plus sum of BJ. And Huang has an explicit form for those triples I, J, K, the eigenvalues need to satisfy. And he conjectured that these are the relations which is also sufficient. As long as the eigenvalue, as long as those ABC satisfy all those relations, then you can find the two matrices A and B, which has AN and BN as their eigenvalues. The sum is given by Cn. And this Huang's conjecture was proven by Newton et al. In a famous paper around 2000. Since this is a probability seminar, so we will consider the randomized version of those two problems. Like the randomized version for the Huang's problem. So it's to study the eigenvalue distribution of U n U star plus V B n V star. So the empirical eigenvalue is just 1 over n, sum of delta lambda I, which are the eigenvalues of this sum. And here U and V, they follow the Haar distribution on the unitary or orthogonal group. So this is just to study the eigenvalues of some of two matrices with eigenvalues given by An and Bn, and the eigenvectors are completely random. And as mentioned in Ali's talk, this one was started, it's known that the empirical eigenvalue distribution, this guy, it converges to the free convolution if the eigenvalues of An converges to mu A, and the eigenvalues of Bn converges to mu B, then the empirical eigenvalue it converges to the free convolution mu A plus mu B, proven by Voiculescu. Actually, he coins this term free convolution, which is sort of very similar to the independence in the classical probability setting. So thanks to this result, we know that the empirical eigenvalue distribution is not uniformly distributed on this polytope given by the relations of Huang. In fact, it's concentrated around this one point given by the free convolution. Actually, Voiculescu proved more. He actually showed that the joint law for these two matrices, UAN, U star, and VBN, V star, they converge to non-commutative free variables A and B with a trace tau. Because these two matrices, they don't commute, so their limits will not be commutative. And the convergence is in this sense. So if you take any non-commutative polynomial P at as a polynomial of U, A, N, U star at V, B, N, V star, you take the normalizer trace, take the trace and normalize it by 1 over n. And this guy will converge to tau PAB. And the free here is somehow very similar to the independent in classical probability theory, which just means that in the limits, take any polynomial of A, subtract its mean tau PA, and times a polynomial Q of B, subtract its mean. And after their product, after subtracting their mean, the expectation tau equals 0. And if A and B are free in this sense, the law of their sum is given by this free convolution. And recently, the probability density of the joint eigenvalues of UAN, U star plus VBN, V star, they are derived and studied by many people, like especially Zuber, Forrester, and their collaborators. They have explicit density for the eigenvalue distribution supported in this polytope. However, the expression is pretty complicated, so I will not show you the expression. And similarly, we consider the randomized Horn-Schur theorem, which is to study the diagonal distribution for the matrix U, A, N, U star, where U follows the Haar distribution on the unitary or orthogonal group. We want to study the empirical measure for the diagonal entries, so 1 over n, sum over delta U, A, N, U stars, IS entry. So for this problem, I have showed you in the slides that the diagonal entries of U, A, N, U star, the IS entry, you can have the explicit formula. And because of the concentration, you can easily show that this quantity, it concentrates around its mean, which is given by trace of AN times 1 over n, the normalized trace of AN. So if we know the empirical eigenvalue distribution of AN converges to this mu A, then this quantity will simply converge to the integral of x with respect to mu A. And this is true for any diagonal entries. So all the diagonal entries, it converges to the same number. So the empirical measure of the diagonal entries, it will simply converge to a delta mass at the point integral of x with respect to mu A. And it turns out the probability density for this guy, it was started long time ago in symplectic geometry setting. And it's known, it dates back to Dauster, Metz, and Hickman. They have explicit formula for the probability density for the diagonal entries of U, A, N, U star. Although we have a probability density for those two objects, however, those probability densities, they are pretty complicated, and it's hard to do any asymptotic analysis. And the goal of our work is just to develop some tools to study the large deviation principle of those two measures. So let me quickly remind you the proof for the standard large deviation principle, which is also used in Ali's talk. See, if we are given a sequence of random variables S1, S2 until Sn, for example, they are in Rd. For example, Sn is just the IID sum of x1, x2 until xn and divided by n. So the way to prove the large deviation of Sn is somehow to tilt the measure by an exponential moment generating function. See, such that under the tilted measure, the real event of S1 will become a typical event. See, if the probability law of Sn we denote it by P, then the tilted measure we denote it by P theta, which is just the moment generating function e to the inner product of theta with Sn. Theta is any vector in Rd we will choose later, and normalize to make this a probability density, and normalize it by expectation of this guy. So we want to choose some theta such that if we want to estimate the probability Sn is close to S, then this guy will be P theta. Under the probability P theta, Sn is close to S, at times the expectation of e to the theta Sn over e to the theta Sn. And because Sn is close to S, under this indicator function, we have this denominator, it becomes approximately given by e to the theta S. And this numerator is just some number, we can factor it out. See if we can choose some theta such that under this theta star, this Sn is close to S, this becomes a typical event. See if we roughly have under this tilted measure, this has probability order 1. Then this will give the large deviation of P at S. See, so we can take log and divide it by some rate function Rn. Then the first term, take log and divide it by 1 over Rn. This will goes to 0 as n goes to infinite. So what's remaining is just the log of expectation of the moment generating function, subtract the inner product of the theta star with S. Then we get a large deviation at S. See, if we want to carry out this argument in our setting for random matrices, Then we need to figure out, see, for example, if we have a sequence of orthogonal or unitary invariant random matrix Xn, like it's just a U an U star or U an U star plus V bn V star. So we want to figure out what is the moment generating function we can use to tilt this random matrix. Then we can do exactly the same thing as for the classical setting. Since in the classical setting, we use the inner product, the most natural generalization is to use the inner product for matrix, which is just a trace of the product of two matrices. See, if we want to study the diagonal distribution of Xn, so we can simply tilt it by e to the beta n over 2 times the trace of Xn yn. So here we use the same convention, beta equals 2, when Xn is a complex Hermitian, and beta equals 1 when Xn is a real symmetric. And this is just trace Xn yn is just an analog of the inner product of theta Sn in last slides. And then we need to normalize it to make this a probability measure. And for the eigenvalues of Xn, it turns out we need to do something slightly more sophisticated. Since the eigenvalues are conjugation invariant, so we can conjugate Xn by any unitary or orthogonal matrix W in 1. The law of eigenvalues of Xn will not change. So this guy in 1 will become, we conjugate Xn by W, it becomes trace of Xn, W, Yn, W star. And because the law of Xn is unitary or orthogonal invariant, so P, W, Xn, W star will have the same law of Pxn. So we still have Pxn here. Because this object is independent of W, so we can choose W to be any unitary or orthogonal matrix. So we can just average it over all the unitary or orthogonal matrix, just integrate dW using the Haar distribution. And it turns out to study the eigenvalues of Xn, we need to tilt the measure use this object, which is the spherical integral.
Can I ask, so what is so you're talking about Xn, what is Yn in this slide?
Oh, so Yn is just a diagonal matrix, like the theta in last slides, we will choose later to tilt the measure of Xn.
Oh, I see. So in the equation 1, you're defining a tilted version of the measure.
Yeah, tilted version of measure is dependent on this Yn. You can think this matrix Yn is some parameter we will choose later to tilt this measure of Xn.
Okay. And in the second displayed equation, you're defining two different versions of tilted measures, or?
Oh, so the second one, yeah, we will use the second one, this guy, to tilt the measure of Xn when we want to study the eigenvalues of Xn. Just take any Yn and tilt it by this integral.
Okay. Why is this the right thing to?
Yeah, I will show you soon
Okay.
why this is the correct object in our setting. Yeah, thank you for this clarifying questions. Yeah. Any more questions? So this object, actually it's called the spherical integral. So given any two matrix Xn and Yn, this integral is the integral of e to the beta n over 2 trace of Xn u Yn u star du. If Xn is a complex Hermitian with the beta equals 2 and u follows the Haar measure on the unitary group. If Xn is a real symmetric, then this beta will be 1 and u will follow the Haar measure on the orthogonal group. Actually, you have seen the rank 1 case of this spherical integral in Ali's talk. In fact, if you take this Yn to be the diagonal matrix, which is just the theta 0, 0, it only has the one entry, which is the theta, other entries are 0. Then this trace of Xn u Yn u star, it's just simply, it becomes just the theta times the inner product of u, Xn u star, no, Xn u, and u is just the first column of this matrix u, so which follows the uniform distribution on the unit sphere. So this is a spherical integral in Ali's talk. The spherical integral is related to the matrix valued Brownian motion in the following way. See, if we start from matrix A, and then we replace each of its entry by a Brownian motion and normalize it by 1 over square root n. Then we have this matrix valued Brownian motion, dAt, which is 1 over square root n dBt. The bt, when beta equals 2 for the complex case, bt will have the complex Brownian motion entries up to the symmetry condition. And when beta equals 1, then bt will be the real Brownian motion up to, will have entries which are real Brownian motion up to the symmetry condition. And it turns out for this matrix valued Brownian motion, its eigenvalues and eigenvectors, they are decoupled, they are independent. So you can integrate out the eigenvectors. Then you get the dynamic for the eigenvalues of AT, which is also called the Dyson's Brownian motion. This was first derived by Dyson. The eigenvalues of AT, they are governed by those stochastic differential equations, d lambda I equals square root of 2 over beta n dWIT. Here WIT are just the independent Gaussian independent Brownian motions for I from 1 to n. And you also have this drift term, which is 1 over n, sum over dt over lambda I, subtract lambda j. Here sum is on the indices j over all the j, which is not I. Here is a plot for the Dyson's Brownian motion if you start from matrix A, which has eigenvalues concentrated at those 2 points. So you get the Dyson's Brownian motion, it's just spread out. As you can see from this simulation, those paths, they don't intersect with each other. It's because of this drift term, lambda I minus lambda j, 1 over. When 2 eigenvalues, they get close to each other, this drift term will make them to repel each other. And so the eigenvalues, they will not intersect with each other. And in fact, in the special case, when beta equals 2, this is also the Brownian motions starting from A, and then you condition them to be non-intersecting. And one gets a spherical integral if we further condition on that at time t equals 1, those eigenvalues are given by B1, B2 until Bn. Like if we start from A, which has eigenvalues all at C0, at the condition at time t equals 1, the Dyson's Brownian motion also ends at every particle at 0. Then we get this very famous watermelon shape plot. And also you can start with A, which has eigenvalues concentrated at 2 points at t equals 0. And its condition at time t equals 1, or the eigenvalues are at this 1 point, then you get this weird shape. And I mentioned that you get the spherical integral in this way. It's because when t equals 1, the matrix valued Brownian motion A1, it will have the same law as A plus G, which G is GOE or GUE. See, we can do an eigenvalue decomposition for it and write it as a U, B, U star. Then because G is a GOE or GUE, then the density for the matrix G will be this guy, e to the minus beta n over 4, trace of G times G star. This trace of G times G star is just the sum of entry square, so which is just the density for the Gaussians. And because A1 is A plus G, so we can do either change of variable, replace G by A1 minus A, and here dG becomes dA1. And then do this, then because A1 is U, B, U star, so the trace of it, we have a trace of A1 square gives trace B square, trace of A square here, a trace of A1, A, it gives a trace of A, U, B, U star, and dA1 becomes du, B, U star. And then we can write this explicitly as dB du, which will give us a Jacobian term, which is bi minus bj to the power beta and product over I and j. We also see this change of variable in Ali's talk. And now if we further condition on B, then this part, this Jacobian, and this trace of a squared plus b squared, it becomes just some constant. So what's left is just the integrand of the spherical integral, trace of a u b u star du. So as you can see, this provides another interpretation for this spherical integral. This is the same as the eigenvector distribution of the A1, condition on that eigenvalues is given by B. And thanks to that relation, the large deviation principle for the eigenvalue distribution of A1 will give the asymptotics for the spherical integral. See, if we know that probability mu A1, the eigenvalue distribution of A1 is close to some mu B. So explicitly, it's this integral over the ball mu A1 is close to mu B. And we have in last slides showed you that this integrand, we can write it as this object. And when B is close to mu B, so this is just some constant, we can take it out. So what's left is just the integral over the matrix U. So in this way, if we know the large deviation principle for the eigenvalue distribution of A1, we know the left-hand side, then we also know the right-hand side, which is the spherical integral. And using this relation between the matrix Brownian motion and the spherical integral, in the paper by Gianni and Zitoni, they showed that if we are given two sequences of diagonal matrices AN and BN, with the empirical eigenvalue distributions converging to mu A and mu B respectively, then the spherical integral take log and divided it by 1 over beta n squared. It has a limit given by some functional I mu A mu B. This functional is kind of complicated since in their proof, what they did is they first derive a large deviation for the Dyson's Brownian motion for the dynamic, and then project it to time t equals 1, which gives the large deviation for the eigenvalue distribution of A1. And use this relation, they get this functional I. And in our talk, we will use this asymptotics for the spherical integral to study the large deviation of those randomized Schoenhorn problems and randomized Horn's problem. So the first main result we get is for the diagonal entries of U, AN, U star. See, let AN to be the sequence of deterministic self-adjoint matrices, such that the spectral measures of mu AN converges weakly towards mu A, and we assume they are compactly supported. Then the distribution for the empirical measure mu N of the diagonal entries of U, AN, U star, it satisfies a large deviation principle with rate function I. So you take log of it and divided it by beta n squared. It's given by minus I mu. So the probability is taken in a ball. Mu n is close to mu in a delta neighborhood of mu. Here, the metric, you can use any metric which is compatible with the weak convergence. And here the rate function I mu is given by the sup of another object h mu nu. Here sup is taken over all the possible probabilities. And h mu nu is given by this guy, 1/2 integral of t nu times t mu, subtract the asymptotics of the spherical integral I nu mu A. Here t nu, for any probability measure nu, this is just the inverse of the cumulative distribution function of nu, which is a increasing function defined from 0, 1 to r. So I want to emphasize that actually this rate function I is pretty good. It's convex and it's proper. And more importantly, it characterizes this polygon. If mu is outside this polygon, then I mu is infinite. This is because this probability will be 0. So this will be minus infinite. And inside this polytope, this rate function is always between 0 and less than infinite. And this rate function, because it takes value 0 only at this one point, which is a delta mass, which is also the limit of mu n. So this is the result for the diagonal entries of U, A, and U star. And we have also the result for the empirical eigenvalue.
There's a question from Reda. It says, in your theorem, the presence of the map T suggests that optimal transport plays some role. True, false? Can you make a comment?
Can you repeat? Sorry.
The question is about the fact that this T, this inverse cumulative distribution function, is arising. Is there a relation, a role played by optimal transport?
In our proof, we didn't use the optimal transport, but it's just a parameterization. I will show you how we get this T mu and T nu, but in our proof, we didn't use anything from optimal transport. Maybe the optimal transport will provide a better understanding of this I, but we don't know.
And I had another question, which is, so I guess what you're saying is that this rate function is infinite on the exterior of this pentagon, you know, whatever the actual shape is, and finite inside, but that doesn't actually rule out there being solutions to the Horn, Schur problem outside, right? It's just that they would need to have an even smaller probability. Is there a way to use your methods to actually establish the conjecture that was subsequently proved a long time ago? But
I think here it's more like the infinite. So here we consider the problem like the infinite version of the Horn-Schur's problem. See, if you have you have to replace this an by the operator a, and then consider the rotation in the non-commutative space and define the diagonal entries for that object. So for that limit object, I think it follows from our theorem. There will be nothing outside this limit of this polytope. But this theorem does not say anything about the finite case.
Okay, thanks.
Yeah, for the some empirical eigenvalue distribution mu n of U A n U star plus V B n V star, we don't have a complete large deviation principle. The result is like this. If A n and B n are sequence of deterministic matrices with empirical eigenvalue measures converges towards mu A and mu B, then we only have the large deviation upper bound. So they'll take log of probability mu n is close to mu, and again normalize it by 1 over beta n squared. This is less or equal than minus I mu. Here, similar to the last result, I mu is given by the sup of H mu nu. And H mu nu, this time it's explicitly given by this combination of the spherical integral. And unfortunately for this one, we don't have the full large division. We only have the complementary lower bound if mu is in the set of measures obtained by free product over amalgamation, which I will explain later. So we see if this is the polygon given by the limits of the Horn's relations, we only have this equality is only true in a subset of it. And we do know the relation cannot be true for the whole domain because we cannot see those boundary conditions from this rate function. It's different from last slides. We can see those boundary curves from the rate function. So in the next 25 minutes, I will show you how to the main ingredients for the proof. For the upper bound, it's very similar to the argument given in Ali's talk, which is pretty straightforward. So we take Yn to be the diagonal matrix, so which we will choose later, and the spectral measure of it converts to mu y. So if we want to have the large deviation upper bound for the eigenvalue distribution of this A plus B, then we have the probability of mu n is in a neighborhood of mu. Then we just multiply those spherical integral both in the numerator and the denominator. So basically we didn't do anything here. And because mu n, it's in a small neighborhood of mu, so this A plus B, the the eigenvalue distribution is close to mu. So we can have use the result by at least at the Tony which gives asymptotics for this spherical integral, which is given approximately by e to the minus beta n square I mu y mu plus little 1. And then what's left is this numerator integrate of it over the ball b mu. Then we have the upper bound by simply replace the integral over the ball mu by the whole integral. Oh, also, I want to emphasize here the expectation is with respect to the u at v, integrate them over the unitary or circular group. So we can first integrate out u at v and then w. When we integrate out u at v, because they are unitary or circular invariant, we can absorb this w into u at v. So simply we can ignore this w. So we have this expectation with only this integrand. Then we replace it by the integral over the whole domain. Then we have the first term gives it's a spherical integral I mu y mu a, and the second term is I mu y mu b. So this is the reason we use this spherical integral, because this quantity we can compute it explicitly. In practice, you can replace this spherical integral in any object you want. As long as you can compute the asymptotics, then it will give you some upper bounds. But the harder part is to get the matched lower bound. Then we can optimize our choice for mu y, take infimum over all the probability measures on the right-hand side. It's still an upper bound. Then we get, after take log and normalize it by 1 over beta n square, we get this minus I mu. I mu is the sup of this object because of the negative sign in here becomes the sup of this object. Then we get h mu y, which is the combination of the spherical integral. So this gives us upper bound. So in the next, we will get the matching lower bound, which is the harder part. So if you look at this proof, the only place which results in inequality is here. We replace this integral in a neighborhood of mu by the whole integral. So the equality will hold if under this tilted measure tilted by this object trace of yn u an u star plus v bn v star under this tilted measure. If we can't get the empirical eigenvalue distribution mu n of this sum, it concentrates around this mu, then we will have when you replace this integral by the whole integral, maybe you will lose some multiplicative, some constant factor, and then take log and normalize it by 1 over beta n square. You basically, the error goes to 0. So you get the matched lower bound. So I want to mention that if you take yn just to be 0, so you don't do any tilting, then you get the mu n is concentrated on this free convolution. So actually, this trivially give you the large deviation at this free convolution point, and we get I equals 0 here. So now the problem, it becomes to study the empirical eigenvalue distribution of u a n u star plus v b n v star under this tilted measure. So we have the explicit characterization of this eigenvalue distribution mu n under this tilted measure given by the free products over amalgamation. However, unfortunately, it seems we cannot use it to get the whole polytope described by the relations of Horn. Actually, we have that the joint law of u a n u star, v b n v star, and yn under this tilted measure. They convert to the non-commutative variables a, b, and y with this trace tau. We have an explicit characterization of this limit objects a, b, and y. So I will show you how to characterize them. So to characterize them, we first study the marginal distribution of u, a, n, u star at yn. Just ignore the second part. Then the integrand, this becomes the integrand of the spherical integral. So the first step, we characterize the joint law of Yn, U(an) U star under this spherical integral, and show that they converge to the non-commutative variable a and y with the trace tau. So to do it, it's since we know from I mentioned in some previous slides that this spherical integral corresponds to the non-intersecting Brownian bridge from Yn to An. So you get this spherical integral by condition on the Brownian bridges from Yn to An, and condition on that they don't intersect with each other. So it's very similar to the Brownian bridge. See, for example, if you consider the Brownian motion from A to B, and there's at time t, there's another description of the law. It's simply given by a Gaussian random variable with mean given by the interpolation from A to B, and plus the mean zero Gaussian, which has variance square root t times square root 1 minus t. So similar here, the non-intersecting Brownian bridge, we have a very similar description at the time slice t. Turns out the particle distribution, it has the same law as the eigenvalue distribution of the interpolation of the two matrices, t times U(an) U star plus 1 minus t times Yn, and plus square root t times 1 minus t times GOE or GUE. So in this way, since we know from the large deviation estimates, we know the profile, the mu t, it converges to some limiting profile. So we know this object under this spherical integral, under this tilted measure, the law of this object converges to some limiting profile. So it does give us some information about this matrices U(an) U star and Yn. And for example, we will know the sum to the c power k and takes a normalized trace. We have this kind of observable. However, those kind of observables are not enough to completely characterize the joint law of Yn and U(an) U star. And to further process, we need to use this so-called loop equation. Turns out for any non-commutative monomials p in the variable y and a, we have that the polynomial p times Yn U(an) U star subtract U(an) U star Yn. This is just the commutator of these two matrices Yn and U(an) U star. So p times this commutator, the normalized trace, it equals the normalized trace of the non-commutative derivative of this p with respect to a. This non-commutative derivative of p, it's given by this expression. So for any copies of a, p contains, we can write p as p1 times a times p2. Then the derivative will give two terms. One is a p1a tensor with p2, subtract p1 tensor with a p2. And the sum of it for each copies of a in this p. And this normalized trace is just a normalized trace of p1a times the normalized trace of p2, subtract the normalized trace of p1 times normalized trace of a p2. So if you use this relation 2, it tells us how to commute this Yn and U(an) U star. So imagine if you have any polynomial in terms of Yn and U(an) U star, you can repeatedly use this relation to commute Yn and U(an) U star, and then you will reduce it to some expression which has Yn comes first as U(an) U star. So something like Yn to the power k times U(an) U star to the power L. And those quantities, we do know them from like this sum to the power k. So these two steps, they completely characterize the joint law of Yn U(an) U star. So in this way, we have a and y, the joint law of a and y. So question p is a polynomial of one or two variables. So here p is a polynomial of those two variables, both y and a. Like it can be like a y plus a or y times a star times y star, something like that. Yeah, so far any more question? Okay. So in the first step, we characterize the joint law of U, AN, U star at Yn. And similarly, if we ignore the first part, we can also use the same thing to characterize the Yn at V, Bn, V star. So in this way, we get the marginal distribution. We have the law of A with Yn and also Bn with Yn. And also, if you look at this tilted measure conditioning on Yn, this density just split into two parts. So U, AN, U star and V, Bn, V star, they are independent. So by passing to the limits, we also expect the same kind of independence, which is called the free with amalgamation over Y. This is the analog for the conditionally independent in the classical setting. So we roughly expect for any polynomial P, so PAY subtract its conditional expectation on Y, tau PAY condition on Y, and the Q, any other polynomial QBY subtract the conditional expectation over Y. As the whole product, you take conditional expectation over Y, it equals 0. So this combined with the marginal distribution of AY and BY, they completely characterize A, B, and Y. And to prove this, we first prove it for discrete mu Y. So mu Y consists of a discrete delta mass, and then use a continuous argument to show this is true for any measure Y. So in this way, we get that all the measures actually we can get is from the limits the law of A plus B, which is given by the free with amalgamation over Y. So this is the proof for the case of A plus B. And for the case for the diagonal entries of U, A, and U star, so the picture is slightly better. We actually have a full large deviation. As you can imagine, we can do a same tilting of measure and get the large deviation upper bound. And in this case, we will tilt the measure, simply use this spherical integral. And the same as in last example, the only place which will give us inequality is when we replace this integral of the diagonal empirical measure of the diagonal entry close to mu, replace it by the integral over the whole domain. However, if we can choose some Yn such that under this tilted measure, mu n is concentrated around mu, then we can have equality here. And it turns out for this case, we can, for any measure mu, which is in the polytope generated by A1, A2 until AN, we can always choose some Yn such that under this tilted measure, the diagonal entries, its empirical measure, will be concentrated around mu. So this will give us a full large deviation. We will both have a large deviation upper bound and lower bound. So to prove the empirical measure, to prove this claim, so similarly, we will use this large deviation upper bound to prove this guy. Using the large deviation upper bound, we have mu n is close to mu, is upper bounded by this minus sup of this functional h mu. And for any mu inside the polytope generated by A1, A2 until AN, we can show that this sup is always achieved by some mu, use some kind of a compactness argument. And moreover, we can show that this mu is uniquely determined by this nu, which achieves this sup. So the map from mu to nu is injective. So to show that mu is uniquely determined by nu, in fact, we use this fact: if nu is the sup, then it's a critical point for this functional. So we can take the derivative with respect to nu, then we get the equality, which characterizes the critical point. And also that relation also gives a relation between mu and nu. Then by analyzing that relation, we can show that actually that relation uniquely characterizes mu. So in other words, the mu is uniquely determined by this nu. Then if this is true, we can show actually under this tilted measure for any mu prime, if we take the mu yn, which converges to nu, then we have under this tilted measure for any, the probability mu n is close to mu prime. Actually, it's exponentially small. Because for any mu prime, this probability is exponentially small as the whole set is compact. By a cover argument, we can show this measure it must concentrate around the mu. Then we get the equality. Then we get the equality here. So for this one, to show this is exponentially small at any mu prime. First, we can simplify this expression by, because mu n is this denominator is the spherical integral. So we get I nu mu a. Here mu yn converges to nu. And for the numerator, because mu n is close to mu prime, which is the empirical distribution for the diagonal entries of u and u star. And the law yn is just a diagonal matrix with measure converges to nu. So this trace is just the diagonal entries of this inner product with diagonal entries of this guy. This will give us the integral t mu prime times t nu. That's how we get this t mu times t nu in this rate function. And what's remaining is this probability mu n is in a neighborhood of mu prime. And for this probability, we can use this large deviation upper bound. So this is upper bounded by minus sup of nu prime, h mu prime, nu prime. Thanks to this observation, mu is uniquely determined by nu. We know this supremum cannot be achieved at nu. Otherwise, there will be mu at mu prime, which gives the same nu. So it gives a contradiction. So we know this supremum it cannot achieved at nu. So the sup it must be bigger than h mu prime nu plus some little constant c. And these two terms, they cancels out, then we get e to the minus beta cn square. So in this way, we conclude that this expectation in a small neighborhood of mu prime is exponentially small. And this is true for any mu prime, which is not mu. So we get actually this tilted measure for mu n, it must concentrate around mu. This gives the full large deviation for the diagonal entries of u, a, and u star. And one can use the same method to consider the quantized version of those problems, like the quantized version of this u, a, and u star, and the quantized version of u, a, and u star plus v, b, and v star. Actually, it will give us some large deviation for quantities related to sure symmetric polynomials. Since I almost run out of time, I think I can stop here. If you are interested for those quantized versions, those large deviation for quantities related to sure symmetric polynomials, you can check out our paper on arXiv. Thank you.
Well, thank you very much. Let me see. So now you can unmute yourself to give a round of applause to Jiaoyang for his talk. Maybe not. And so.
Oh, I saw a question. It asked, would anything similar be possible to do with GSE or different betas? I think we can, for beta equals 4, in our case, it will correspond to GSE. And for GSE, there's also matrix models for it. So we can do exactly the same thing as we did for unitary or circular case. I generalize it to the symplectic case. However, for general beta, because there's no matrix model for our problems we consider, so we don't know if we can consider them or not.
Okay, so I have a question. So about this method of these spherical integrals. I mean, only recently learned the power of this idea of transforming this quadratic term into linear terms, multiplying by taking expectations with respect to, for example, to the Gaussian in the statistical physics models. So in principle, these ideas permit to do the same type of things in the matrix realm, or one should be more careful to.
Oh, I feel this idea is very similar to the idea which used in like this kind of argument. If you have some square, then you if you want to compute something, if you want to compute some linear object like this one is linear in A and B, right? Then you introduce some Gaussian, then it becomes the integral of the Gaussian. I think this kind of argument, it might be possible to study more involved. This is basically just a two matrix model. We have only A and B. It might be possible to use it to study multi-matrix models to do more complicated matrix integrals. I think Alice has some work in this direction. But always for the matrix fitting, because of the long commutativity, the estimates are more lasty than the classical fitting.
Okay, so there, it seems that there are more questions in the chat.
I think Retta had a question about
yes.
LDP for measure valued paths upon multiple convolution. I don't know if Retta, you want to explain more? But...
Sure. So I can say more like out loud. So you have these relationships like that when you do like multiple like convolutions, like somehow like the Still-Just transform that satisfies some Burger's equation. And I was always like wondering if there's some LDP version of this so that you could get from getting like multiple convolutions, like you add, and then you get some LDP for the path of measures. And the minimums should be given like by the complex Burger's equations. So you have these works by like Matitsin and that Alice Guillaunet and Ofer Zaytouni like did in a very rigorous way. So I don't know. I'm just asking if there's a relationship like to this previous work.
So do you mean like consider like a UA1 U star plus UA2 U star plus UA3 U star?
Exactly. So you just make multiple sums and you look at the path. And yes, like the path.
This is a dynamic, right? For
yes.
So we add it's like you want to add every time you add something which is infinitesimally small something.
Yes.
So basically for this long intersecting, for this guy, the matrix valued Brownian motion, basically every time you add a small yes. GOE, and this guy, the limiting profile, it's characterized by the complex Burger equation.
Yes.
I can imagine in the model, it's a very interesting model you mentioned. There might also, if every time you add something which is pretty small, maybe it's possible to have some scaling limits use this kind of argument to get the limiting profile.
Yeah. So because I think so that
it's given by the free convolution, right, in that city.
Yes.
And really to somehow take some limits. So the thing is, for this guy, every time slice, it's the distribution is the initial distribution free convolution with a semicircle distribution, and the semicircle distribution gets bigger and bigger. But here, if you also condition time t equals 1, the distribution, then the whole thing is given by the complex Burger's equation, which is somehow more involved than this case. This case is basically, I think it's after some. So this one you basically can only converge on at the infinite. This particles goes to like behave like square root t. At this you don't condition on the endpoint. At the model you mentioned, if you don't condition at the endpoint, then maybe it's just a free convolution with a lot of measures. But if you consider UA1 U star plus UA2 U star until like a UAM U star, and then condition on the whole sum, the law of the whole sum, maybe you can get something like more like the complex Burger equation. Like
Okay.
I'm not sure.
Okay. Okay.
Very good. So if there are no questions, let's see if we can thank again Jiaoyang for his talk. So you may be able to unmute yourself now.
Okay, and we'll see you all next week. Shurov will speak. I don't think it's on the subject at least wants him to speak about, but it'll be interesting. We'll update the website with the abstract and title.
See you everybody next week.
See you next week.